Today we'll be talking about waves and just giving ourselves, telling ourselves the basics of waves, right? So a wave is an oscillation or vibration accompanied by transfer of energy that travels through space or mass. The space or mass is called a medium. Now, um, going further, a medium is an intervening substance such as air or water through which a wave can transfer its energy. Based on those two things, let me cite an example. Take for instance, you have a bowl of water that is just a bowl of water. It's still water. It's not moving. Take another drop of water in your hand or any form of thing. The moment now drop just a drop from your hand. Let it make contact with the one in that bowl. Now the moment the water in your hand makes contact, the drop of water in your hand makes contact with the one that is in the bowl. Now a vibration takes place, right? That vibration is actually the wave. Now the wave now transfers energy, and that water becomes a medium. So the wave transfers energy through the water, which is a medium. That is why when you drop it, you will see ripples, small circles, small, big, big, bigger, and so on and so forth. So what is just happening is that, and one thing you should also know is that the energy is actually transferred, but the medium doesn't move along. The medium is just there, because what you discover is that the water will just experience a form of swelling. That when it swells, it goes back to its former position, and so. That's why when rain wants to start dropping somewhere, if you watch some of these films or if you've seen some analysis, when water drops, rain drops, let's use that. Now once rain drops, you see that ripples are formed in different areas. The water is actually swelling, the medium swells. This medium doesn't move, but it is just the transfer of energy that you are seeing. So please, let's take note of that. This is another perfect example. Now this is actually trying to say that, give us an example that these people you see here, they are like they are all on they are all on top of an ocean, right? And a big object hits that ocean. Now these people, they are attached to that water, they are not moving. So what will happen here is that the moment that big object touches that water, there tends to be a vibration, which is the wave. Now, that wave, that wave moves, transfers energy to that water, which is a medium, and causes the water to swell up. So these people, you will see that they will experience some form of swelling or something. They will just you look as if some of them will go up a little and come back to their former position, and so on and so forth. So we want to quickly go to types of waves. Now, please let's not forget, waves are mechanical because they move. So anything that moves has the mindset of mechanical. Let's start with talking about transverse waves. Now, a transverse wave is a wave vibrating perpendicular to the direction it is traveling. A transverse wave is a wave vibrating perpendicular to the direction it is traveling. Now, from the diagram you see here, you will notice that there is this sort of movement, there is this sort of sine wave movement. Because if you are familiar with your graph, when you are doing a sine graph, it's not always straight, it's always curved like. So it's kind of curved like. So the wave is having a sine, it's form of a sine curve. Let me just I can call it sine wave or sine curve. So the wave is having that form. So that's why you see that there's this form of upward downward movement. Now the straight line you are seeing there is called the equilibrium point of that wave. Now the truth is that when a medium, let's say water, when it swells, the moment the swelling, the water comes up, when it experiences that wave, the moment the experience of that wave is over, the water tends to be still, and it's in a kind of straight position. So that straight position is also called equilibrium position. That's why you are seeing this line that you have here. So like I said, a transverse wave vibrates or travels perpendicular to the direction it is traveling. It vibrates perpendicular. Please, let's not forget that. So two waves that are transverse is actually your light and your water waves. Light wave and water wave, they are transverse in nature. I will still get to the part where I explain what these two standing things and arrow is. Now the truth is that these transverse waves, they are a kind of wonderful type of waves. I will still give more analysis on what I'm saying. Now, let's quickly talk about some parameters, right? Now, the equilibrium. Now we are talking about transverse waves and parameters that are some kind of words that are attached to transverse wave. Now this is the equilibrium. Now this is the midline of a wave, the medium of the wave's resting position. So this is the position. I said this few seconds ago or few minutes ago that that position is the position where the wave, where where that particular medium is at rest. Wave happens to the medium. Please do not forget that. Let's know what a medium is and what wave is. Medium is the receiving, is the receiver of the wave, right? It's the receiver of the wave. So the medium of that, the resting position of a wave is called the equilibrium. Now there's also something called crest. Now let me quickly talk about something. There's something called crest and trough. Now put it this way, look at it this way. If you watch films or if you've had the chance to go to mountains, you discover that these mountains, they have mountain tops and they have valleys. So and this mountain top, they have peak, they have a peak, right? So let's take the crest as the highest point of a wave and the trough as the lowest point of a wave. Now there's also something called wavelength. Now a wavelength is the distance between two successive crests and two successive trough. Two successive crest and two successive trough. Remember I said the crest is the peak, the highest point, while the trough is the valley. Let's call it a valley, like lowest point. Now we also have amplitude. This is the distance between a crest or trough and the equilibrium point. There's a diagram that is coming shortly. You will see it and you understand. Now please, I want you to also know that the more the amount of energy, the more the amplitude. The bigger the energy, the amplitude. Let me cite an example. Imagine a sea. Imagine a sea. A sea, like, okay, imagine like a river. No, not a river. What will I call, what can I use now? Okay, imagine a still water. Imagine a still water. Look at these two things. A human being falling on that water and a big stone falling on that water. What will happen? When a human being falls, there will be a wave, but the wave, the amplitude of that wave will not be compared to when a very large stone falls on it. So please take note that the bigger the energy, the higher the amount of energy, the more the amplitude. The bigger the amount of energy, the more the amplitude. Yes, let me use this example to explain what a transverse wave is. Now, in this guy tied a rope to a kind of ring on a wall. He tied it to that wall, and he wanted to flap it. He wanted to flap it. Now, I want to use this to explain what a wave is. Now, you see this dotted line. It is the equilibrium position. That before he started doing this, he held the rope. He held it straight. He held the rope straight. So so that straight position is the resting position, the equilibrium position. Now the next thing is crest. I said crest is the highest point. So these two lines, this green part is what tells us that this top part is crest. With this you can also recognize other crest. This is one, this is two, this is another crest. Now, okay, now this is also the trough. Now the trough is the lower part. Now the amplitude is the distance, please pay attention, the distance between the straight line and the trough. Is also the distance between, you see this, all these red lines, that straight line is the amplitude, the distance between the equilibrium position and the trough, and also the distance between the equilibrium position and the crest. So from one crest to the equilibrium position, from the equilibrium position to another crest, to another trough, sorry, the crest is at the top, the trough is down. So the distance between the equilibrium position and the crest is called amplitude. So like I said, the bigger the amplitude, the bigger the energy, sorry, the bigger the amplitude. So that is more and more analysis on what I'm saying. So wavelength is now the distance between two successive crests and two successive troughs. So you see the I think the brownish or the orange like color you have there, where you see the arrow joining two crests together, telling you that that is the wavelength. Now this is an example. Now we are now asked to determine the number of crest that is here and the number of trough, and also determine the wavelength. Let's analyze. We said crest is the peak point. So this is one, this is two, this is three. So there are three crests here. Let's count the number of trough. One, two, three. There are also three trough. But if you notice, if you want to count as crest, this is one, two, and three. There is a half here. So you have 3.5 crests. If you want to count the trough, one, two, three. One, two, and three. There is also a half here. So this is 3.5 trough. Let's now count the wavelength. Now we said the wavelength is distance between two successive crests and two successive trough. Now this is a trough, this is a trough. Now the two troughs you have here, it shows you that this is one wavelength, two wavelength. So this is 2.5 wavelengths. One, two. This is not a full one, so this is 2.5. That's in terms of trough. In terms of crest, this is one, two. There's also a half here, so this is 2.5 wavelength. Please let's know that. So that is just the analysis of it. Yes, that is still what we are saying. The number of crests. Now I forgot to say something. I forgot to talk about a node. Now a node is the distance when the equilibrium point is crossed, right? The equilibrium point is crossed. Now this wave started from here and moved down. I'm talking about this particular first crest, this one that is forming a crest. It moved down. Now when it moved from here to here, this distance now is called a node. Please let's not forget that. Now the next type of wave is called longitudinal waves. Now there's a note on this in the school website. Please look at it and understand more of what I'm talking about here. There's another one called longitudinal waves. Now longitudinal wave is also called compression. It's also called compression wave. Now I said it's a wave vibrating in the same direction. Remember, transverse wave, they vibrate what? Perpendicular, while this one vibrate in the same direction. Some textbooks will tell you that they vibrate parallel to, but please know that they vibrate in the same direction as they are traveling. Observe this. Let me cite an example. Observe this, that like these are particles that are moving. So if you look at this point, this black point, those are the parts where there are compressions, right? Those are the parts where there are compressions. So a longitudinal wave is a wave vibrating in the same direction as it is traveling, and sound waves travel in this pattern. Sound wave is a perfect example of longitudinal wave. So let's talk about the parameters contained in longitudinal waves, which is compression and rarefaction. Please, not refraction, not refraction, not diffraction, but rarefaction. Compression, a region in a longitudinal wave where the particles are closest together, while rarefaction, a region in a longitudinal wave where the particles are further up, they are furthest apart. They are kind of far from each other. Now the wavelength here is now the distance between two consecutive compression or two consecutive rarefaction. Now this diagram is a perfect example. I'm using a string. This is a spring, like a spring. That's what I'm using as example. So this is the compression here, and this is the rarefaction. So the distance between one rarefaction and another rarefaction, please forgive me, rarefaction is the wavelength. So the distance between one compression and another compression is wavelength. This is the rarefaction. This is another rarefaction close towards the end. So the distance between this and this gives you the wavelength, while the distance between this compression and this compression gives you the wavelength. So please, that is just the idea of this. Please, thank you for listening. God bless you.